This is the third video on section 3.2. And for example 79, we're being asked, does this line intersect this plane? So we're given parametric equations of a line, we're given the equation of a plane, and we want to know if the two intersect. So what do? Well, we take the equation of our plane, x plus 2y plus z equal to 4, and we substitute for x 1 plus 2t. For y, we substitute negative 2 plus t, and for z, we substitute 5 minus 4t. And now we just have a linear equation in terms of t that we solve for. When we solve for this, however, when we combine like terms and simplify, all the t terms cancel, and we end up with the equation 2 equal to 4, which is of course a contradiction, which means there's no solution. Since there's no solution, the line and the plane do not intersect. Example 80, we're given two planes, and we want to find the equation of the line where they intersect. And there are a couple different approaches to this, and I will show you one and explain the other. So we start with the equations of these two planes. And this is a system with two equations and three unknowns. And what you're going to learn in linear algebra, that such a system will either have no solution or infinitely many solutions. Here we're assuming it has infinitely many solutions because we're assuming these two planes intersect in a line. If they don't intersect, well, we'll find that out as well. So what we're going to do is we're going to set z equal to 0. So setting z equal to 0 for the first equation gives us 2x minus y is equal to 1. What this is telling us is this plane here is intersecting the xy plane in this line. For this plane here, we set z equal to 0 as well, and it gives us this line. So this plane intersects the xy plane in this line. So now we have two lines in the xy plane. We're going to find the point of intersection of these two lines, if it exists, and it does. Notice we have a negative y and a y here, so we can just add these two equations together. That will give us negative x equal to 8, and so x is equal to negative 8. And now we substitute. We do what we call back substitution. X is negative 8. We substitute in one of these equations to find y is negative 17. You might want to substitute in both just to check your answer. X is negative 8. Y is negative 17. Those were found under the assumption that z is 0. Remember, we started off by setting z equal to 0, so z is still 0. Okay, so now what do we have? We have a point where the two planes intersect. Now we need a vector. Okay, a couple different options here. We can play this game again. We could set another variable equal to 0 and then find another point of intersection. And then we have 2 points, and we know how to find the equation of a line that contains 2 points. We did it in the previous video. That's one approach. I'm going to show you another one. What we really need, though, is a point and a vector. Finding a second point is just another way of finding a vector that is parallel to the line. So let's find that vector another way. Well, let's look at n1. n1 is 2, negative 1, 3. Where did that come from? That's the normal vector to this plane. Remember, to find the equation of a plane, you need a point and a normal vector. Our normal vector is the vector 2, negative 1, 3. The normal vector to the second plane is negative 3, 1, 5. So these are our two normal vectors. These are both orthogonal to their respective planes. So we take the cross product of these two vectors. The cross product is orthogonal to both vectors. That means the cross product right here is parallel to each plane. These vectors are orthogonal to their respective planes. N is orthogonal to both of those vectors, so n is parallel to the both planes. It's parallel to the line of intersection where the planes intersect. So we take this n as our direction vector. So we just write the parametric equations of the line. X is negative 8 minus 8t. Y is negative 17 minus 19t, and z is 0 minus t. When t is equal to 0, we have the point negative 8, negative 17, 0. When t is equal to negative 1, that kind of makes our math a little nice. When t is equal to negative 1, then we have the point 0, 2, 1. And you can check that the point 0, 2, 1 is also on each plane. So 0, 2, 1, 0, 2, 1. You can see that that point satisfies both of these equations.